Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. We are from Group 10. We would like to present about ferroaluminium alloy. First, let me introduce myself. My name is Rizky Zulim Pratama. My teammates, they are Ahmad Daniel Hakim bin Muhammad Azizan, Julian Arman, Muhammad Ashraf bin Muhammad Kurdi, and Nur Azra Fatini binti Aslansyah. Iron and aluminium combine to form the ferroalloy known as ferroaluminium. Ferroaluminium is used in the deoxidation of steel, harvesting, thermal reactions, aluminium nickel cobalt magnets, alloying additions to welding wires and plugs, among other processes. The metal typically contains 40 to 60% aluminium. The alloy is also well known for producing low melting point alloys and performing aluminothermic welding. In general, ferroalloys may be divided into two categories. First, bulk ferroalloys, and second, specific ferroalloys. The three main ferroalloys are made of silicon, manganese, and chromium. For the chromium, it offers a number of benefits, including good corrosion resistance. Then, the physical properties of ferroaluminium alloy. For the compound formula, it is FeAl. Then the molecular weight is 82.83, and it appears in gray powder or granules. For the melting point, it is at 1250 degrees Celsius. The density of ferroaluminium is 5.56 gram per centimeter cube. The exact mass is 82.916 gram per mole, and the monoisotopic mass is 82.916 gram per mole. Then we continue to mechanical properties of ferroaluminium alloy. From the table, we can see that Fe2Al with the largest shear modulus and Young modulus is the hard phase. Fe2Al5 with the smallest modulus is the soft phase. FeAl, Fe3Al, FeAl3, FeAl2, then Fe2Al5 with the lower B or G values are considered to be ductile materials. Fe2Al with the lower Poisson ratio value of 0.274 is brittle material. There are some applications of ferroaluminium alloy. First, incinerators, then protective coatings, so that the turbine components of a turbocharger, and also the construction materials.
Assalamualaikum and hello. My name is Julian Arman and I will continue the presentation. Phase diagram of FeAl alloy. A phase diagram is a type of chart used to show conditions at which thermodynamically distant phase. So this is a phase diagram of FeAl alloy. Isothermal reaction. There are two properties for isothermal reaction. To identify isothermal reaction, look at horizontal straight line and V-shape on phase diagram. Intermetallic. For intermetallic compounds formed in FeAl, there are FeAl2, FeAl3, Fe3Al, FeAl, and last is Fe2Al5. Solid solution. A solid solution is a solid-state solution of one or more solids in a solvent. Eutectic reaction. Eutectic reaction is a type of reaction in which, on cooling, liquid phase will transform to solid phase at the same time. Based on FEL phase diagram, eutectic reaction will occur at 52% AL at a temperature of 1155 degrees Celsius, where liquid will transform into Fe2Al5 plus Fe5Al8 epsilon. Eutectic reaction. Eutectic transformation is a type of transformation in which, on cooling, one single solid phase will transform into two other solid phases at the same time. Based on FeAl phase diagram, eutectic reaction will occur at 44% Al at a temperature of 1102 degrees Celsius, where epsilon will transform to FeAl and FeAl2. Peritectic reaction. Peritectic transformation is a type of transformation in which on cooling, the phase one of them is liquid will transform into a single new solid phase. Based on FeAl phase diagram, peritectic reaction will occur at 28% Al at a temperature of 1310 degrees Celsius, where epsilon and liquid will transform into FeAl. Peritectic reaction. Peritectic reaction is a type of transformation in which on cooling, the solid phase will transform into a single new solid phase. Based on FeAl phase diagram, peritectic reaction will occur at 49% Al at a temperature of 1155 degrees Celsius, where Fe2Al5 plus Fe5Al8 epsilon will transform into FeAl2. That's all from me. Next presentation is Azra.
Thank you, Julian. Good day, everyone. I am Azra. I will be presenting the first type of ferroaluminium alloy with 10% aluminium. According to this binary phase diagram, at high temperature, or to be specific, at temperature above 1530 degrees C, the alloy only exists in liquid form. As the temperature decreases to 1530 degrees C, alpha ferrum solids start to growing in the liquid. That's when the solidification starts to happen in region 2. At temperature 1530 to 1500, then alpha ferrum will continue its habitance to form a complete microstructure of alpha ferrum permanently. The solidification process of this composition of alloy can be presented in cooling curve as shown in the slide. And from this curve, we could determine its cooling range at 1530 to 1500 degrees C. Next, how about the mass fraction of the phases exist at 1520? For 1% of aluminum at 1520 degrees C lies on the region of 2 where alpha ferrum and liquid exist. In order to determine both mass composition, we apply lever rule and find the value of A and B, where A is 3 and B is 1. Calculation is resulting at 1520 degrees C. Ferroaluminium alloy exists in both phases as mentioned before. 75% liquid and 25% alpha ferrum.
Assalamualaikum and hi everyone. My name is Ahmad Daniel Hakim bin Muhammad Azizan, and for my turn I'm going to discuss about iron aluminium alloy with a composition of 30% weight percentage aluminium. Okay, when we take a look at the line plotted, we will know that the alloy exists in liquid form around 0.1. After that, when the temperature went down around 1394 degrees Celsius, alpha starts to go in liquid form. This process continues until the temperature reaches 1310 degrees Celsius. As this happens, we can notice at the microstructure that the alpha liquid phase changes slowly in FeAl liquid form. At last, when it reaches 1300 degrees Celsius, the phase will form completely into FeAl structure. Okay, on the next slide, there's a cooling curve that we can see and can relate it with the explanation that I've described for the previous slide. Now let's move on to the composition at 1394 degrees Celsius. Okay, at this temperature with the weight percentage of 30%, we can determine that the phases present in the region are alpha and liquid. Next, by the use of the lever rule, calculations of the mass composition can be obtained. So the mass composition of liquid after calculating it is 100%, while for alpha is 0%. Okay, from this we can conclude that the FeAl alloy still exists in liquid form at 1394 degrees Celsius. Hence, the alpha will start to grow in liquid below that temperature.
Based on this phase diagram, it can be seen that in region 1 at temperature 1500 degrees Celsius above, the alloy is only exists in liquid form. So going down at temperature 1310 degrees Celsius, solidification process starts. At temperature around 1300 degrees Celsius, in region 2, it changed to FeAl liquid form. Solidification ends at temperature of 1232 degrees Celsius. Below the temperature of 1232 degrees Celsius, only FeAl exists in this range until 800 degrees Celsius. It is in region 3. At temperature 800 degrees Celsius, FeAl and FeAl2 is about to form as final microstructure of 33 weight percent aluminum, 67 weight percent ferrum alloy. The solidification process of this composition of alloy can be presented in cooling curve as shown in this slide. To determine mass composition, we apply lever rule to find the value of A and B. After that, we put that value to the formula mass composition. Hence, at 600 degrees Celsius, barium aluminum alloy exists in two phases, which are 88.49% FeAl and 11.76% FeAl2.
Hi and good day. My name is Muhammad Ashraf bin Mat Kurdi, and I am going to explain about iron aluminum alloy with a composition of 44% weight percentage of aluminum. Now, the red line here indicates the composition of alloy, which is 44% weight percentage of aluminum. Starting from point 1, the alloy will only exist at liquid phase. As the temperature goes down and reach 1220, which is here, epsilon will start to form. If you look closely on the microstructure, epsilon will start to form and it will grow larger and larger until it reaches a temperature of 1200, which is here. In between the temperature of 1200 and 1102, only epsilon will exist in the microstructure. Once it reaches a temperature of 1102, which is eutectoid temperature, lamellar structure consists of FeAl and FeAl2 will form in the epsilon microstructure before. Then it will grow larger and larger during this constant isothermal temperature, and once it reaches a certain time, only lamellar structure consists of FeAl and FeAl2 will exist. This is the final microstructure that exists in the room temperature. If we take a closer look at the microstructure drawn at point 4, FeAl and FeAl2 will arrange alternately. This is what we call as lamella, which I have been discussed earlier. Now, to have a better understanding, let's take a look at this cooling curve. As the temperature decreases along this line, liquid will only exist. Then, once the temperature decreases to 1220 degrees Celsius, epsilon will start to form in the liquid. Then, the temperature will decrease along this line and the epsilon will grow larger and larger until it reaches a temperature of 1200 degrees Celsius. At this temperature and at this point, fully epsilon is developed. All the remaining liquid is fully transformed into epsilon, and between 1200 and 1102 only epsilon microstructure will exist. Then, when the temperature reaches 1102, the lamellar structure of FeAl and FeAl2 will start to form in between epsilon. This microstructure of lamella will grow larger and larger upon time, and once it reaches a certain time here, the only microstructure that exists is lamellar structure of FeAl and FeAl2, and at the room temperature only this microstructure will exist. And now we could calculate the composition of this alloy at 800 degrees Celsius. At 800 degrees Celsius, with 44 weight percentage of aluminium, the phase present here is FeAl and FeAl2. Then by applying level rule, we could calculate the mass composition of these phases. So the mass composition of FeAl is 26.67% and mass composition of FeAl2 is 73.33%. Then if we add up these two numbers, we could get 100%.
The diagram phase of 80 weight percent of aluminum and 20 weight percent of ferrum. First, the solidification process of 80 weight percent aluminum and 20 weight percent of ferrum. From the diagram, there are three phases 1, 2, and 3. At above 1030 degrees Celsius, FeAl exists in liquid form. Then at 1030 degrees Celsius, FeAl3 start to form as temperature decreases. FeAl3 will grow larger until T equals to 655 degrees Celsius. And then at T equals to 655 degrees Celsius, Al will start to form inside the FeAl3 microstructure. Finally, the microstructure consists of FeAl3 and Al exists at room temperature. So for the microstructure, we can see that the first phase is the form liquid or the liquid form. Then it changes to liquid plus FeAl3. Then Al will exist to it, so it becomes Al plus FeAl3. Then we continue to cooling curve. For the cooling curve, we can see that the temperature is decreased while it formed to the liquid. Then at 1030 degrees Celsius until T equals to 655 degrees Celsius, it changed to liquid plus FeAl3. Then after T equals to 655 degrees Celsius, it formed Al plus FeAl3. After that, we can calculate the mass composition. So I took the temperature at 655 degrees Celsius. So we can apply the lever rule A and B. And I took the 61 point and 98. For the A, it's equals to 80 minus 61, it become 19, and for B, 98 minus 80, it become 18. For the mass composition, we can see at the picture. First, for the FeAl3, it's equals to A per A, I mean B per A plus B. So the result is 88.65%, and the mass of Al is 19 per 19 plus 18, it becomes 51.35%. So at 655 degrees Celsius, Fel alloy exists in two phases, which are 80.35% of aluminum and 48.4% 65% of FeAl3.
One of the methods of improving the material properties is by adding a strong carbide former such as titanium, zirconium or cerium. For B2 iron aluminum alloy, addition of carbon will decrease the strength due to the precipitation of soft graphite phase. Formation of graphite can be prevented by adding a strong carbide former. This will increase in the strength and hardness due to the precipitation of hard carbide. As a result, the coefficient of friction and wear rate of iron aluminum based alloy will decrease due to high hardness of titanium carbide and also zirconium carbide. One of the examples of industrial application that use this method of improving is in car industry. Iron aluminum was used to produce the roller axle of the control unit of a turbine in the car that was exploited through 20,000 km. The developed technology allowed a repeated quality of the component with no cracks. If you look at the graph here, the addition of strong carbide will decrease the coefficient of friction, which will decrease the wear rate of a material.
For the second point of methods of improving material properties, we can increase the concentration of transition metal. Okay, by doing this, the minimum creep rates can be decreased. This improvement was attributed to precipitation hardening and solid solution hardening respectively. In the engineering industry, the high carbon alloy has a creep rate versus stress curve typical of oxide dispersion strengthened alloys. Precipitation hardening also promotes the development of steady state creep regime in addition to reducing minimum creep rate. Solid solution hardening greatly decreases the minimum creep rate at high and low stresses. However, the strengthening effect may be weakened after a certain period of creep due to microstructural instability.
In conclusion, by using the phase diagram, we can predict the microstructure of ferrum aluminum alloys, transformation of phases during the solidification process, construct the cooling curve, and determine the composition of phases. Apart from that, adding strong carbide former and increasing concentration of transition metal are two suggested ways to improve material properties, which can provide higher strength and hardness as well as minimize its creep rate. This is the end of our presentation. Thank you for your attention.